Right, this video is on interpreting and working with equilibrium constants, and it's your packet that looks something like this. Okay, so this first section is entitled The Magnitude of the Equilibrium Constant. So a little bit of background information that the equilibrium constants, whether we're talking about Kc or Kp, vary from very large numbers to very small numbers. And the magnitude, which is of course the size of Kc or Kp, it tells us extremely important information about the equilibrium composition of the reaction or of the mixture, so to speak. So we basically have two situations where we have K that is greater than 1, or we have K that is less than 1. And we classify these into two separate groups based on their size. So if you think about a K being greater than 1, and we recall that K is products over reactants, and my K value is bigger than 1, then the situation becomes that there are more products than reactants at equilibrium, okay? And so, for example, if K, I'm just making up a number, if K was 40, well, 40 technically is a fraction, 40 over 1, which means my products are being represented by my number 40 and my reactants number 1. And so I have many more products at equilibrium. So, and when this is the case, it's said that equilibrium tends to lie to the right. Okay, that means the right-handed side of the reaction or the products. So you'll hear that said a lot. Equilibrium lies to the right, and that the products are favored. Okay, at equilibrium. And then of course the reverse is true if K is less than 1. And again, you can think about K being P over R. So let's say you had a equilibrium constant of, 0.02. You can also make that a fraction by putting it over 1. And of course, in this case, which one is bigger? Of course, R is bigger. So if K is less than 1, equilibrium is said to lie to the left. Okay, or the left-handed side of the reaction, and the reactants are favored. So the question, then becomes, why is this important to us? And it could be important for several reasons. If you think about your, goal is to create a lot of product, okay, by manipulating a chemical reaction, then you would want to pick a reaction that had a big K value, okay, because then that means that you're going to make a lot of product. If your goal was to make a lot of product and you pick a reaction to pursue that has a really small K value, well, no matter how much reactant you throw in there, it just doesn't favor the production of the products. The products are going to be created, but not in huge amounts. Okay, so that's where K, the magnitude of K, comes into play. So there's a couple practice questions. We can talk about those real quick. The first one gives you a reaction. It says it's considered a means of fixing nitrogen. The value for this equilibrium constant is 1 times 10 to the negative 30. Holy cow. That is teeny tiny. And the question is describe the feasibility of fixing nitrogen at this temperature. So that reaction above, the N2 plus the O2 making 2NO, that's the reaction. So if you think about where equilibrium lies, if you think about this being P over R, right? Equilibrium totally lies to the left, and you're not going to be fixing very much nitrogen to form NO. So, not many products being created, something along those lines would be the answer to that one. And then if we look at practice number 2, it says for the reaction H2 plus I2 yields 2HI. Kp, here, let me write this down. Kp is 794 at a temperature of 298. And Kp is only 54 at 700 Kelvin. Is the formation of Hi favored more at a higher or lower temperature? So of course, Hi is your product, so the bigger Kp means more favored, and so in this case, the production of Hi would be favored at the smaller temperature because Kp is larger. So fairly self-explanatory in this case. All right, so going onward, the direction of chemical equilibrium in K. Okay, so important point is that equilibrium can be approached from either direction. And we talked about this in class with the graphical representation where we drew the lines. So let's say we have this is the reaction. Okay, both gases. Again, keep in mind I could write a Kc or a Kp for this. So we're going to approach it from the forward direction, okay, which would mean reading left to right. So saying that you have N2O4 in a container and it's going to decompose or break down or whatnot into 2 in O2s. That would be the forward. But I can also approach this reaction from the reverse, meaning I'm reading it right to left, where these are my reactants, okay, and this is my product, so this is creating this. It can be read in both directions, and that's important for equilibrium. So if I approach it from the forward direction, then my Kc expression would, be P over R, which would be NO2 squared over N2O4. Okay, and I could either calculate this value if I had data, or I could look this up. And I looked this up, and this value is 0.212 at, I picked a temperature, 100 degrees Celsius. Okay, so this is the value. So I could ask you a question like, does this reaction favor the reactants or the products? Again, we just talked about this. Put this over 1. It obviously favors the reactant, so I'm going to put a little note here. Okay. But I can approach this reaction from the reverse direction where I'm reading it reactants go to products, okay? And so for that case, then Kc would be the reciprocal. It would be the I don't want to say reverse. Gosh, reciprocal is the correct answer, because if this is my reactant, this is my product, then this is the numerator of my fraction. Okay, now my Kc looks like this. And I can easily calculate this. I don't need to look this up at all. If Kc for the forward is 0.212 technically over 1, then isn't Kc for the reverse the reciprocal of this? Okay, and if you don't like that, of course, we can calculate that. It becomes about 4.7. But again, if I asked you, who does this reaction favor? Okay, well, this is a larger than 1 equilibrium constant, so you would say it favors the products. Okay, and you might be thinking, but wait a minute, how can the reaction favor the reactants going one direction and the products going in another direction? Well, but it's the same species, right? Think about it. So in the forward, when we're saying it favors the reactants, we're saying it favors this. But in the reverse, when we're saying it favors the products, this is the product. So it doesn't matter from what direction we're approaching equilibrium, because the two equilibrium constants are related, okay? As shown with a reciprocal situation, okay? If you flip your page, there's a practice problem. If you would attempt to answer that while I erase the board, and then we'll move on. All right, so the equation gives you, or the problem gives you the synthesis of ammonia and gives you a Kp value, and it asks you what's the Kp for the reverse. So there's not much to this, but of course this is the reverse reaction. Okay, and we just learned that if we're going to do Kp for the reverse, we're going to take the reciprocal. So we're going to take 1 over the Kp of the forward. And again, I can reevaluate that. It becomes about 230. And so there it is. It's as simple as that to find Kp for the reverse reaction. Okay, so you'll always take the reciprocal. What happens to students is that sometimes they get a little bit confused with this idea in a thermochem approach, where we're so used to taking a reaction and flipping it and changing the sign on delta H. And while that's legit for delta H, because remember that's energy in and energy out, that doesn't work for Kp and Kc. And think about it, Kp and Kc can never be negative, so that doesn't even make sense. You can't have negative pressures, you can't have negative molarities. But Kc and Kp are ratios, okay? It's not just a fixed number, and so when they reverse, they become an inverse. So that's a big takeaway. You reverse a reaction in thermochem, you change its sign. You reverse a reaction in equilibrium, and you take the reciprocal of Kc or Kp. All right, there's a couple more things to this relating reactions and equilibrium constants. Okay, so this is your next section. So we just talked about what happens if we reverse a reaction, we take a reciprocal. We can do a couple other things too. So let's go back to this guy. Whoops, that's an N. Okay, gas and gas. So if we wrote a Kp for this, or well, let's do Kc. My paper's Kc, I apologize. Okay, so Kc would be concentration of NO2 squared over concentration of N2O4. And of course I could look this up, or we just did this one on the front, and that value was 0.212. Okay. So now the situation would become, what if I double this? Okay, what happens to Kc? So what if now this was my reaction? Okay. So, again, this is where a lot of times students get confused because they think thermochem. So if we, remember Hess's law, okay, so if we double a reaction in Hess's law, we double delta H because energy is directly proportional to the amount of reaction I have. And so you might be inclined to say, well, I would just double K. Okay, but that's not the case here, because you have to think about how the coefficients play into K, and they're the exponents. So if we wrote a Kc for this, and some of you might see this rather quickly, my placement of my reactants and products are still the same, but their exponents are different. Okay, and you might be able to pick up on the fact that I could rewrite this to look something like this. Technically. Okay, so that's the same thing. So what is going to happen to Kc in this case is it's going to become squared. It's going to be the square of the original Kc for this reaction. So to get this, I would take my 0.212 and I would square that value to get the new Kc value for this. Turns out to be something like 0.449. Okay, so it's not doubled. All right, it's not doubled like energy is in thermochem, it's squared. So you might ask, well, what if you triple a reaction? And so again, if you triple a reaction in thermochem, you would triple the energy, but not in Kc and Kp discussion. If you triple a reaction, you're going to cube Kc or Kp. Okay, so if you multiply a reaction by any number, you're going to raise Kc to that power. So you might want to write that as a takeaway. If you multiply a reaction by any value, you'll raise Kc or Kp to that value. Okay, so if you take a reaction and quadruple it, okay, multiply by 4, then you're going to take the Kc value, whatever that might be, and you're going to raise it to the 4th power. Not multiply by 4, raise it to the 4th power. There's a difference. But this is the takeaway, okay? So you might also be thinking, well, what happens if I divide a reaction? Well, the same rule applies. Okay, if you divide a reaction by any value, you'll raise Kc or Kp to that value. So let's say you divide by 2. Okay, you're technically halving the reaction. Well, you would take Kc and you would raise it to the half power, which is actually taking a square root. Do you know that? I think you should know that. That's actually taking a square root. Okay, so if you divide a reaction by 3, you would take Kc and raise it to the 1/3 power, which is actually taking the cube root of the Kc value. So again, you're not dividing Kc by 2 or by 3. You're raising it to the 1 over that power. That's a little wordy, but that's what you're doing. Okay, and then the only other thing that we have left to discuss is an application kind of Hess's law, but I'm going to save that for a second video because I think my phone is dying.